Okay, so now we get to the theory behind conductors in series and parallel. This will resemble when we talked about resistors in series and parallel in physics 3. So I've covered that topic in chapter 27 and 28 of the book. And it's also similar to capacitors in series and parallel, and I've covered that in chapter 26. And also springs in series and parallel, right? I've covered that in chapter 15 of my lectures. So we have here a conductor K1 with conductivity K1, and we have another conductor K2, right? Then we have T inside and T outside. So now heat will flow. Let's say heat is flowing inside, right? From the outside to the inside. And so the thing to determine is what adds up and what stays the same. So to give an example, I'm going to use one of the topics from physics 3, let's say the resistors in series, right? So if I have a battery and we have here one resistor and another resistor. So these two resistors are in series. So what does it mean to be in series? That means it takes the two resistors to make a complete circuit, and the current flowing through the two resistors is the same, right? I goes through. So the current flowing through the battery is the same as the current flowing through the two resistors. So we can say here I total is equal to I1, which equals I2. And then we have to determine what adds up. Well, the voltage difference across resistor 1 plus the voltage difference across resistor 2 adds up to give you the total voltage of the battery. So we have here V total is equal to V1 plus V2. Then we use the definition of resistance and Ohm's law, right? Voltage is equal to current times resistance, right? So the total voltage will be equal to I total, R total, okay? And then the voltage V1 will equal I1, R1, and then voltage V2 will equal I2, R2, right? And then you can say, well, the total current is equal to the first, the I1 and equals to I2, and so the currents cancel. Then you have here R total is equal to R1 plus R2. So this is how you set up the equation for two resistors in series. Now these two heat conductors are also in series. Why? Because the power flowing through both of them, the heat flowing through both of them is the same, right? P1, P2. Whatever heat flows through the first one also flows through the second one by necessity. So we can say P total is equal to P1, which equals to P2. Okay? Now what adds up in this case? What's the quantity that adds up? Well, the change in temperature from the outside to the inside is, let's call that delta T total, right? The change in temperature from the outside to the end of the first conductor, delta T1, right? And then the change in temperature from the left side of the second conductor all the way to the right side of the second conductor, we can call that delta T2, right? So the change in temperature delta T1 plus the change in temperature delta T2 equals to the total change in temperature. So that's kind of acting as the voltage here. The voltage is being adding up. So we say here delta T total is equal to delta T1 plus delta T2, right? And then let's proceed from there. Therefore, how do the two conductors add up? Well, let's use the equation P is equal to Ka delta T over delta X. Delta X, which is the thickness of both of them, right? I'm just going to call the delta X, delta X1, I'm going to call that L1. In other words, its length from one end to the other end. To make it easy, we'll just call that L1. And then delta X2, we'll call that L2, okay? So now let's isolate the change in temperature here. Let's isolate that. We can say delta T is equal to P, and then delta X is just going to be L, right, over Ka, right? So now we can say delta T total, so delta T total is P total, L total, over K total, A total, okay? And then delta T1 is equal to P1 L1 over K1 A1. And then delta T2 is equal to P2 L2 over K2 and then A2, right? So now the thing to determine is what's the same here? What can I cancel? Well, we already said the power flowing through the first conductor also has to flow through the second conductor. So P total is equal to P1, which equals to P2. So then the P totals cancel. P1 cancels, P2 cancels. Okay, how about L total, L1, L2? Well, the only thing we can say there is L total is equal to L1 plus L2. L total is equal to L1 plus L2, but we can't really get rid of them, so it has to stay. How about A total? Well, the A total is the surface area of this one here, coming out toward you. And then A1 is the surface area of each individual one, A1 this way, and then A2 this way, right? So basically, since they share the same area, the area of the second conductor coming out this way, the area of that is the same. This area the heat coming in this way, the cross-sectional area is the same. The area of K1 is also the same, and it's also equal to the total area. So in this case, A total, A1, and A2 are all the same. So they cancel out. A total, A1, A2. So now we have derived how conductance adds up in a series, right? So the equation for conductance adding up, L total over K total is equal to L1 over K1 plus L2 over K2. Okay? So we can give an example here of how this would work. Have to note their thicknesses, right? The length of each one here, which is actually their thickness, right? So let's just say, to make it easy, let's say for now that they have the same thickness. L1 is equal to 1 meter, L2 is equal to 1 meter. So then how would they add up in series? So then in that case, it will be L total will be 2 meters, right? It's the total thickness over K total, which I don't know what it is equal to 1 over 2 plus 1 over 4. Okay, so then what's that going to equal? Then I can multiply this by 2. All right, so then I'm going to get here 3 over 4. Right, and then you're going to have here, you can cross multiply K total is equal to 2 times 4. That's going to be 8 divided by 3. So that's going to be equal to 2.667 watts per meter Celsius. So the K total ended up becoming closer to the 2, right? A little bit larger than the 2, but smaller than the K2, right? So it ended up being somewhere in between the two, okay? So it all depends on their thicknesses also, okay? So what would happen, let's change this around a little bit. What would happen if the thickness of K1 was larger? Okay, plus 1/4, so what is that going to give you? So that's going to give you 5 over 4. Then you can cross multiply, you're going to get K total is going to be equal to 3 times 4. That's 12 over 5. So that's going to equal what? 2.4. So what ended up happening? As I increased the thickness of the K1, the conductivity came closer to the value of K1. So it ended up that the material is now less conducting. Well, does that make sense? If you make the less conductive material thicker, that is going to reduce its conductivity, right? Because this is now thicker, right? It's 2 meters. And then this is 2 meters here. And this is 1 meter here. So this is conductivity of 2. This is conductivity of 4. So now if this one is thicker, its conductivity is reduced, right? The total conductivity of the material comes closer to the 2, right? So now if we go one more progression of this, right? So that's going to be equal to 2.28, so it's even lower than this. So what's happening? As this thing keeps getting bigger and bigger and bigger, it proves that the total conductivity is approaching the conductivity of the lower one. So as L1 goes to infinity, right? If this one gets infinitely thick, the K total will equal just itself. It will be equal to 2, right? So it'd be like the 4 is not even there. Well, what will happen if I keep the thickness of the L2 the same, and then I increase the thickness of the L2, right? So we can try that. You see what's happening? See, if I make the conductivity of 4 the wider one, the total conductivity starts approaching the conductivity of the 4. So you can see that what's going to happen to the progression of that. If I, as the limit of the K2, the thickness of the K2 gets into infinity, the total conductivity of the material will approach 4, and it will eventually equal 4, right? So now let's define something known as the R value. So remember, the equation was L total over K total is equal to L1 over K1 plus L2 over K2. This one is what's known as the R factor or insulation factor. Insulation, right? So that means the smaller the conductivity of the material, so that means the material is not good conductor, but that means it's a good insulator, right? So the insulation goes up. So for building materials, you want the K of the material to be low and the length of the material to be large, right? So in other words, you want the material to be as thick as possible, and you want the conductivity to be as low as possible. So when this is low and this is large, the R value is large. So these would be good insulators. And if you want the material to be low insulation, then we would of course want the conductivity to be high and the length to be low. So we want the material to be thin, and we want it to be a good conductor, and then the R value will go down, right? So how does the R value of two conductors add up? Well, L total over K total is going to be R total. L1 over K1 is going to be R1, and then L2 over K2 will be R2. So what does that mean? Well, two materials of different conductivity of different lengths, the insulation factor of this plus the insulation factor of this will give you the total insulation. So that kind of makes sense, because if you have two materials, their insulations will add up, their R values will add up. The more materials we put in series, the less heat we will lose to the surroundings. You kind of see this makes more practical sense to write the equation this way than to write it this way. So if we compare this to how resistors and capacitors and springs add up in series, right, quickly, right, so we already said resistors in series add up so that R total is equal to R1 plus R2. So if you have two electrical resistors in series, their total resistance adds up. Well, this one looks like the insulation factor, how the insulation factor of two insulators adds up, right? R1 plus R2. The only difference is that with insulation, it's defined as the L over the conductivity, right? You have this extra L. So now, how about capacitors in series? C1, C2. You can look at the video that I've explained how capacitors add up in series. You will see that capacitors add up like this. 1 over C total is equal to 1 over C1 plus 1 over C2. So you can see here that it resembles how conductors add up in series. The only difference is here, there is no such thing as L total, L1, and L2. The L total, L1, and L2 is already built into the capacitance of the material. Because the capacitance of the material is A E0 over D. So the capacitance already is determined by knowing the surface area of the capacitors and knowing the thickness of each one. So it's already built into capacitance. Whereas here, you have to have the conductivity, and on top of that, you have to have the thickness of the material, L total and L1 and L2. So the equation resembles capacitors, but it has that extra thickness factor, the L total, okay? Now, how about springs in series? If you have a spring like this, K1, K2, and this is the spring constant of the springs. How do they add up in series? Well, it ends up that it's 1 over K total is equal to 1 over K1 plus 1 over K2. So that one is again very similar to how the conductivity adds up, but again, it doesn't have that extra variable of L total, L1, and L2, right? You only need to know the spring constant of each spring, and then this will tell you what the total spring constant of the series is. Okay, now let's talk about how heat conductors add up in parallel. Okay, so again, let's go to resistance and see how we derive the total resistance of the circuit. So we have to determine what adds up. So in this case, the current that comes in, I total, breaks up into two currents, right? Breaks up into I1 and I2. So we have here I1 This is R2, so we have here I1 and we have here I2. So we have I total is equal to I1 plus I2. And then you use the fact that I total is equal to V total over R total. V total over R total. And then I1 is equal to V1 over R1. I2 is equal to V2 over R2. And then you say that the total voltage across each resistor is the same, right? So V total and V1 and V2 are the same, and then you get 1 over R total is equal to 1 over R1 plus 1 over R2, okay? Just to practice, we can also practice the springs. So what adds up and what's the same? Well, the force on each spring adds up, right? But the displacements are the same. So as this mass goes down, each spring displaces the same amount, but the force, the weight of this, mg, is distributed among the two springs unequally, right? So the force on each spring adds up. So we can say in this case, F total is equal to F1 plus F2. Then F total is going to equal K total, X total, F1 K1 X1, and F2 K2 X2, right? Okay, then each spring will stretch the same amount. So X total is equal to X1, which equals to X2. So the X total cancel. Imagine there's a heat conductor like this, K1 and K2, and then the heat is coming in like this. Okay, so what is the same and what is different? Well, in this case, the power flowing through the top plus the power flowing through the bottom is equal to the total power, right? So we say here this is P1, P2, and then the total power is P total. So it's the power that is adding up. The change in temperature from the outside and the inside is the same. So delta T1 and delta T2, they are the same, right? And they are equal to delta T total. So let's now derive the equation. So I have here P is equal to Ka delta T over L, right? So then I have here P total is equal to P1 plus P2. Those are the same. So this one cancels this one, which cancels this one, right? So we do get an equation here. Well, in this case, the L total is the same too. The total length, the total thickness here, and the total thickness of this, L total is equal to L1, which equals L2, right? L total, which equals L1, which equals L2. So that one can cancel out. And then, so we get an equation, right? And then the A total is the total surface area coming out like this, right? The total surface area of the whole wall, like this, that's A total. The total surface area of just K1 would be A1, and then just K2 would be A2. So the surface area of this plus the cross-sectional surface area of this is equal to the total cross-sectional area. So A total would be equal to A1 plus A2. Similar to how the conductors added up in series, in that we had L total in that case, L total, L1 and L2. In this case we have A total, A1 and A2, right? So, and then we can see here, again it's similar to that, C1 plus C2, you see the same idea, but then it's got this extra A factor, which is the surface area, right? So then, how does this work? Let's give it some numbers again. Let's say K1 was equal to 2, and then surface area A1 was equal to, let's say 1 meter squared, and then K2 was equal to 4, and then A2 was equal to 1 meter squared. So we'll give the same kind of numbers that we had before. We had L1, which was equal to 1 meter, L2, which was equal to 1 meter, but now I'm making A1 1 meter squared and A2 1 meter squared. So then what will K total be? So we have here K total, and then the area total would equal 2 meters squared, and then we would have here K1, which was 2 times 1 plus 4 times 1. So what would that be? K total, the 4 plus 2 would be 6 over 2. It would be 3, and then they would have the same units as the K, of course, whatever units that the Ks have. So if they have the same surface area, in this case, the total K came out to be exactly in between the two, exactly equal to 3, right? In the other case, when they had L1 was 1 and L2 was 1, the total conductivity came out to be closer to the 2, right? It came out to be closer to the lower conductivity. In this case, it came out to be exactly in between, right? So then, how about if we make the K1 have bigger surface area? Okay, we went down from 3 down to 2, so it seems to be following the same pattern. As the surface area of the A1 gets larger, it starts to dominate the conductivity of the material, and the K value approaches the value of the K1, right? So what happens as the A1 becomes equal to 3? Right. Continuing, the total conductivity approaches the value of 2. So the limit as the surface area of K1 goes to infinity, then the material's conductivity will equal exactly to the value of K1, right? You will approach the value of K1. So the same thing will happen as I make the surface area of the K2 wider, as it goes to 2, 3, 4, 5 meters squared. The same thing will happen. The total K value will approach to the value of the K2, right? So now you can see how this works. Now, how can we rewrite the equation in terms of insulation factor, the R value, right? So how does the insulation add up? Well, now you have here L total, and then I can bring the K total down here. I can bring the K1 down here, and the K2 down here. Then I can write L total over K total as R total. So then it'll be A total over R total is equal to A1 over R1 plus A2 over R2. So the insulation factor in parallel will add up like electrical resistors in parallel, right? So you can see that if we rewrite the equation in terms of the heat insulation factor, there is a similarity to how electrical resistance adds up in parallel, right? But you have this extra factor that you have A total, the total surface area, adds up, so A total and A1 and A2 are not the same. So you got this extra factor over here, right? Now let's give the insulation factors of different building materials, right? So this is the metric unit system of measuring the insulation factor, and the British unit system of measuring this is going to be equal to feet squared times Fahrenheit times hours over British thermal units. Right? So I'll give you the insulation factor for different building materials in the British unit system, feet squared Fahrenheit hours over British thermal units, and then I'll show you how to convert those to the metric units. Right? So the insulation factor R for hardwood sliding for every 1 inch of the material. So for 1 inch of a hardwood sliding, the insulation factor would be equal to 0.91, and that's in units of feet squared Fahrenheit hours over British thermal units. You can see why fiberglass is one of the materials that's preferred for insulation inside of dry walls. We have a 3.5 inch, which is a little bit less than 4 inches of brick, right? It's even less thick, but it's got an insulation factor of 10.9 versus the brick has 4.0. So the bigger this value, the 10.9, the better insulator it is, and we can use that for insulating the walls of the buildings, right? So then the insulation factor for fiberglass for 6-inch fiberglass will just be a ratio of the length. So 6 to 3.5, that's almost the ratio of 2. So then we can see that the insulation factor will be 18.80. Okay, well, what if the drywall was 3.5 inches? We can compare them. What if the drywall was 3.5 inches? The table gives us the thickness of a drywall that's a half an inch, and it's 0.45. Well, if it was 3.5 inches, 0.5 goes into 3.57 times, right? So we would multiply the 0.45 by 7, and then what would that give us? That would give us 35, 3, 28, 31, so it would be 3.15. So the insulation of this will be 3.15, and the drywall won't be as insulating as fiberglass, which makes sense. That's why you put fiberglass in the middle of two drywalls to increase the insulation even more. So if the fiberglass is 10.9 and this is 1.01, it's about 10 times less, right? So it's 10 times less insulating than fiberglass. So you don't want to have just air. You definitely want to put fiberglass or other material in between two drywalls to increase its insulation factor, right? So then we have the insulation factor of glass. The fiberglass board is really good because if the fiberglass board was 3.5 inches, right, which would be three and a half times that, times 3.5, right, then it would be about 12, 14, 15, something like 15. And then that would be even bigger than the regular fiberglass, right, which was 10.9. This would be 15. So the 3.5-inch fiberglass board will have a really good insulation power, right? Now let me show you how to convert from the British unit system to the metric unit system. We'll just give one example, right? Let's say the fiberglass, the 10.9. Then I can convert 1 foot is 12 inches. 1 inch is 2.54 centimeters, right? 100 centimeters is 1 meter. Right, so 1 foot will, I have to square this, right? Because this is foot squared, I would have to square the foot is 12 inches, that would get rid of that. 1 inch is 2.54 centimeters, I have to square that. The inches squared will get rid of that. 100 centimeters is 1 meter, I have to square that. The centimeter squared will cancel that, right? And then I can multiply, I'm going to get rid of the British thermal unit. 1 British thermal unit is 1055 joules. So the British thermal unit will cancel that, and then 1 hour is 3,600 seconds. So the hour and the hour will cancel, right? And then we just have seconds. And then how about the conversion between Fahrenheit and Celsius? Well, remember the equation, Fahrenheit is 9/5 Celsius plus 32. So 1 change of Fahrenheit is equal to 9/5 change of Celsius, right? So the Fahrenheit and the Fahrenheit cancel, right? So you can see for a 3.5-inch fiberglass, the 10.9 that it had for the insulation factor turns out to be 6.22 in metric units, right? What if the thickness of the fiberglass was given to you in meters or in centimeters? Let's say you were told that there is a 2-centimeter fiberglass, right? Then what would you do? What would its insulation factor be in the metric unit system, right? This insulation factor 10.9, which is equal to 6.22, was for a 3.5-inch fiberglass, right? Then we would have to find out if this is given in centimeters, we would have to convert from the inches to the centimeters, right? So we'll now convert from there. I can say 1 inch is equal to 2.54 centimeters, and then the inch cancels the inch, right? Then I multiply this by the actual thickness of the fiberglass. So I get here 2 centimeters, right? So look at what happened to the units. The inches canceled the inches, and the centimeters canceled the centimeters, right? So when I multiplied all this out, this canceled that, and then so the total units of that would be meters squared Celsius for watts, and this would be for 2 centimeters of fiberglass, right? So depending on what the problem is saying, if it's a 3.5-inch fiberglass, we can use the 6.22 version, or if it's a 2-centimeter fiberglass, we can use the 1.4 version. And so now you know how to convert between the 6.22 and then to arrive at the 1.4 answer, okay? So now this gives you a good example of how to add up resistors in series and parallel, how to express the answer in the insulation factor, and then how to convert from the insulation factor of building materials to the metric unit system. And thank you very much.